Okay, so I hope everyone's ready. So moving on to the actual presentation. Okay, so this is the agenda that I'm going to share today. So most of the time will be spent on the case studies of ModusTest KGS being used in the field in actual customer site. And I'll spend some time going over ROI analysis for you guys. And I have some data for install-based analysis. And I'll share some of the new offerings, exciting offerings that we have at ModusTest. And then we'll go through Q&A after that. So let's watch the animated rendering first. So this is one of our testers, XT, with 16,000 channels. So you're looking at the tester at the bottom and cycle at the top, the golden part that's called regular shorting device to be inserted into the actual package. And the test is performed. So that's an animated rendering of one of the testers we offer. Basically, using this, you can perform system level per pin Kelvin CRS measurement. So you're going to be measuring CRS on Kelvin method on every single pin in the socket, and we have up to 29,000 channels. That's a new offering we have. I go over that a little bit later, and it has high accuracy of plus minus 1 millim. And I want to emphasize that this is an application-specific housing, which means has the same dimensions and everything as your actual package size. So this test is performed as if it's used in the real production environment. And you can also perform system lifecycle test, system FDR. FDR stands for force, distance, and resistance. And I have more details on that. And open short leakage test. And I also share those of you who are developing or using coaxial socket. We have a coaxial socket test. And you can also perform or build your interface board based on multi-site or multi-footprint. And I have a sample picture for you. And you can also perform temperature characterization on your sockets. These are the case studies I'll be sharing today. I have two major sections under case studies. First one is for the socket developers mainly, and then engineers who choose looking for best optimal socket for their application. So first section is called socket design validation selection and OQC. OQC stands for outgoing quality check. And I have two examples, one called system lifecycle test, and the second one is system FDR. And after that, I'll be going over production performance improvement case studies, including failure isolation on yield issues and marginal failing pins isolations, and cleaning recipe development, and coaxial socket testing, as well as design validation. The last item, the coaxial socket design validation actually belongs to the first category, but because it's a coaxial topic, I went ahead and placed it under production. So the last one is a power VCC pin area drop analysis, but that's TBD. Okay, so let's start with a socket design validation. And this is a typical socket validation selection outgoing quality check process flow for most of the socket suppliers, especially the ones who do not have ModusTest KGS. So basically what happens is when they develop new socket, they go through characterization using per pin analysis, and also some kind of generic housing design validation. Okay. And then if it passes, goes through production, and a lot of socket suppliers, they perform days chain outgoing quality check before they send out the sockets to their customers. So some challenges with this process are first, because it's not in the actual application-specific socket, along with a few reasons. We believe it's a less than optimal performance measurement. which also leads to less than optimal socket selection because you're making decision based on the data that you are seeing in terms of the performance of the socket. And another challenge with this process is because if you're still using a date chain OQC, there's a possibility of marginal pin escapes because you're looking at the whole chain of a pin measurement instead of looking at individual CRS performance of each pin. So we have observed less than optimal socket data along and as well as socket selection. And we have observed marginal pin escape issues with this current process. So when you add ModusTest KGS process in this, a couple of advantages are you get to perform application-specific housing system-level design verification. So you're performing characterization on your socket as if you're running in the real production environment. That's the second bullet, production emulated lifecycle test. And also you can perform application-specific housing system FDR validation. A lot of our customers, they perform outgoing OQC using ModusTest KGS. And this allows only system level verified and confirmed known good socket to be shipped to the customers. And let me share two test cases about this process. So first one is called socket design validation. This is a life cycle test that was performed on one of the sockets. So on the y-axis, it's resistance measurement, and x-axis is number of the pins. So in this particular example, the socket had around 1,400 pins. And each of these dots, a color dot means insertion. So this blue means that's at zero, time zero or zero insertion measurement. And the gray means at 100,000 insertion. So ModusTest KGS lifecycle test confirmed a mean CRS of less than 90 million on all pins, including I/O, power, and ground pins over the 100,000 cycles in a few days. It took us a few days to perform 100K without having to use a production setup. I've also worked in different factories. One of the challenges there to qualify the new socket was, using the actual production setup to perform this analysis, actually with live packages. And it takes days to reach the amount of insertion that we wanted to see during that DOE evaluation. But with ModusTest KGS, you can perform all of these analysis outside a production environment, and it only takes a few days to perform it. And on the data set, you can also see that after 1K cycles, the mean and standard deviation CRS reduced and improved, and this is a typical spring pin behavior. And this is a 3D map plot over after 100,000 cycles shows acceptable CRS measurement on all pins. And this is a 3D. You can also see the shape of the package that was tested. And there are some areas with a little bit higher CRS measurement after 100,000 cycle, but they're still at the within the acceptable range of CRS measurement. Okay. Moving on to the second test case study. This is called System FDR for Socket Handler and Setup Optimization. So for those of you who are not familiar with FDR test, so basically you are putting a force on your socket, compressing, actuating the socket or the pins, and there's a displacement as you push this down. And then you measure the resistance of each pins. So that's how the test is performed. In this particular example, ModusTest KGS FDR was performed on the socket with 300 micron per pin working travel distance in the datasheet. So that's what the datasheet says. So it's it says you have 300 micron working travel distance. So on the graph, let me explain some of the lines here. So on the first axis on the left, that's a test force, the force applied on top of the socket. On the right side, that's a mean CRES value of all pins. And the blue line is test force. We're actuating the socket, right, with higher force. And this purple line shows mean CRES measurement on all pins versus Z down. So this point is indicates minimum force that requires to make all pins contact, right? Because if you have any pin that's not making contact, it'll read infinite resistance. That's what you see there. So as soon as you see a meaningful number, CRES measurement, so we can see that that's the first contact where all pins are making contacts. And we continue to press the socket down until we reach hard stop of the socket. So that's the distance. And then we continue to perform system level CRES measurement on this socket. So what do we learn from this exercise? We learned that working travel distance of the pin at system level in real application socket is 160 micron versus 300 micron per pin in the data sheet. So how do people use this information? So KGS, ModusTest KGS confirm the actual working travel distance is 160 micron versus 300 micron in the data sheet. And this is useful, very critical for contactor and stack-up validation, and also handler setup optimization for your team in the factory. Okay. Yeah. So those are the two major examples that I've shared for the socket validation, and I'm moving on to the production side. So this is a typical production line without ModusTest KGS. Unfortunately, things happen in production line, right? Even if it's yielding, the socket's yielding, product is yielding, when those sockets come back to the shop, you will actually have quite a number of pins either walking wounded because of the environment it was exposed to in the production, or you'll have marginal pins coming back from production line. And as I mentioned before, if the daisy chain test was performed at your socket supplier site, you will have some, not much, of there's a possibility of receiving marginal pins as when you receive the new sockets from the vendor. So those are stored in the hardware shop, and they are released to production when production starts testing, and that causes low first pass yield, low final test yield, and yield variation, site to site, tester to tester, even factory floor to floor, different variations, and which also causes high retest rates. And you will recover, but then you're wasting a lot of tester resources performing retest, and which causes low OEE issues, utilization issues, and long setup and debug time. And whenever your setup goes down, which means you have really low yield and you have to fix it, conventionally, what's happening in the factory is they either use blind or visual inspection or limited test data based partial, because some of the nowadays, I guess most, you can say a lot of chips come with a CRES test on IO. So it has a partial, although the accuracy is not good enough to understand the performance of the socket. It does have some level of CRES test on partial IO. There's no coverage on power and ground pins, and which drives either pin cleaning or replacement of the pins to fix the setup that's down. And because of limited access to the data, inaccurate and ineffective problem solving happens, and you either end up under or over cleaning the pins, which also drive the cost of the pin and socket high. And I'm pretty sure if you worked in the production floor, you can relate to this cycle, right? Ineffective problem solving leads to continuous low utilization, long cycle time, low throughput, you name it. It's almost like a vicious cycle going back and forth. So that's what a lot of people on the production floor face. And let's look at process flow with ModusTest KGS in the picture. So sockets are supplied by the sent by suppliers, and also they are coming back from production floor. I said this is optional because usually at the beginning of implementing ModusTest KGS, some of our customers require 100% test at the incoming, so they can also compare test result with outgoing test result from their suppliers. But eventually, they make this either sample or optional. Okay, so they perform incoming test, but all of them make sure they have outgoing test out of their hardware shop before any sockets reach production floor. So they perform the ModusTest KGS to identify either failing or marginal pins and screen them out, and they make sure that only known good sockets are provided to the production floor, which result in higher first pass yield, final test yield, and less yield variation, low retest rates, higher utilization, and optimized setup and debug time, and therefore optimized cycle time and higher throughput. And the setups go down. It does. We don't live in perfect world, but when setup goes down, now they're using ModusTest KGS to perform the analysis, which helps them to instantly find failing pins or marginal pins. It allows them to save good pins because some test or some pins do not require very low series performance, and you can also customize a limit. You can save some of the still good pins on the package in the socket. And you can also develop smart cleaning with a recipe development. And I have a specific example for test cases for each of these later. And you can also perform common failure analysis for continuous setup optimization. What I mean by that is if you see, let's say, one corner of the package continuously going bad, you either have a setup issue, planarity issue, or you may even have a package planarity issue. So with the data set you are collecting from the failure analysis using ModusTest KGS, it allows you to perform a next level problem isolation. So overall, ModusTest KGS allows only confirmed known good sockets to stay in the production line. Let me go through the real example of those issues or cases. So first example I want to share is it's one of the customers we had, and they has had the following issues with multiple generations of products over several years. I think it was about 7 years. They're having continuous issues with this. So they had issues with multi-site yield variation, setup to setup, subcon to subcon yield variation, and they had high pin replacement costs because they kept on replacing the pin, and low first pass yield and high retest rate. Okay, so it was ongoing. These are the remedies applied by the team in the factory. So they actually developed automated laser cleaning tools for the sockets because they were getting so many sockets to be cleaned at a very frequent, high frequency. And they also developed, as usual, they developed labor-intensive process control to minimize yield variation, such as pin cleaning and replacement maintenance schedule, and socket replacement and load board cleaning and replacement. And as I mentioned before, they're basically going through this cycle for 7 years, trying to optimize their production throughput. And yeah, there are some positive effects. It was getting better, but they were still struggling back and forth. And I want to emphasize that this is not the only example. This is like one of the good examples that I'm sharing with you, but there are multiple cases like this. So I try to think of some analogies to explain this. So I think good example is trying to fix your knee injury without an MRI. Okay? Because they don't have access to the data they need to understand the root cause of the issues. And another good example is for test engineers out there, trying to debug your test program based on go, no-go, pass-fail results without having access to the scope. So what did we do with ModusTest KGS? So we actually put a scope in the socket that measures CRES on every single pins in the socket. And it revealed that mean and standard deviation of the CRES measurement have increased significantly only after 23,000 insertion. And that was the sample they gave us when we first got there. And they informed us that these are brand new pins, which is reading below 100 million. And these are the used pins. They have 23,000 insertions. So we took the measurement. And as you can see, there's a difference between these two. And if you know about the socket, this should not happen. I mean, these sockets should last over 100,000 insertions easily, but they're seeing this kind of shift in the socket CRES measurement. So we took the next step, and we came up with a DOE to perform analysis on CRES measurement. Surprisingly, we found out that this shifting of CRES measurement was happening only after 400 insertions, right? And, basically same signature at 23,000, but it was happening, at the very early stage of the life of the pins. We're like, wow, this is not right, okay? And we perform additional analysis on this measurement, and we found out that so this is a brand new socket, this U socket. These shifts are happening on the pins, specifically on power ground pins at the middle of the package, at the center of the package, as you can see on this image. So that's where the power ground pins are located, and that's where shifts were happening. The pins around the edge with high-speed interface didn't have that issue. Okay? And the further analysis revealed that SAM revealed there was I couldn't get the real image because IP issues, but I portrayed it. So SAM revealed diffused extra layer buildup on power and ground pins due to high temperature and current coming from their product with lead on the solder ball and the type of pin tip metal alloy they were using. They used to build this particular pin was causing this diffuse extra metal layer. And that's why laser cleaning could not remove entirely this layer. And that's why there was a shift in the CRES measurement causing yield variation all over the places. So our recommendation was to replace existing pins with a new type of pins to prevent layer buildups. And we recommended them to continue to use ModusTest KGS in socket validation and selection in the future. This is a snapshot of our 2D and 3D images of the socket. So ModusTest KGS identified failing pins. So these are depend on the color coding that you can customize based on the resistance measurement. So you can see these are the red ones are failing pins. Display them in 2D and 3D. This allows operator. It doesn't take. Another nice thing about this tool, it does not require test engineering skills. Operators can identify quickly either failing or walking wounded marginal pins to replace them and put them back on production floor. And as I mentioned before, this also will enable engineers to identify package planarity or handler setup issues if you find one of the areas with much higher resistance consistently. Moving on to developing cleaning recipe. These are the two examples of actual example of developing cleaning recipe. On the left-hand side, so the y-axis shows test insertion. So what we did was after every 10 cycles of actuation in the socket, we measured CRES, okay, using silver device. This is not cleaning coupon. Therefore, you don't see any changes both here and also on the graph on the right. The second part of the graph is 50 cycles. So after every 10 cycles of cleaning coupon, we measured CRES. This is on 20-gram pin. This is on 27-gram force pin. So as you can see, 27-gram pin shows much better performance of cleaning using same material, but then you have much better result of cleaning the socket. This is a top-down view, or I guess bottom-up view of the socket pin, the CRS measurement in color. So this is before, after, no change. And this is at 27 gram before and after. You can see how well it was cleaned at this. So we concluded, ModusTest KGS concluded that cleaning coupon with 40x insertion on 27 pin would be an ideal recipe for this particular product. So without this, so typical consequences without ModusTest KGS is you will have continuous yield issues, even though you're cleaning, if you're not using the right recipe due to the ineffective cleaning, and also non-ideal recipe to shorten, because if you end up over cleaning, you will actually shorten the lifespan of the pins. So that's why we called it a smart cleaning recipe. You can customize your cleaning recipe per product using our tool. Next example is coaxial socket testing. So let me try to explain the concept of coaxial socket. For signal integrity, they developed coaxial socket to shield your signal pins with the ground body. So that's what this is about. So shield performance is impacted by the DC resistance of the connection from VSS to the shielding body. Because that's how signal pins are shielded. However, the issue is, unlike a pin tips connection, which is designed for high PSI point of contact to achieve low CRS, this pin to housing is not typically designed to achieve high PSI contact point. Therefore, it results in resistance values typically so if with good contact, you should have very low resistance measurement. However, because of the fact that it's prone to wear, and also the presence of oxides and foreign materials such as lubricants and cleaning solvents can cause these two point to not to be disconnected, but cause extra resistance between the barrel, shielding body, and the VSS pin. And also, depending on the location of your signal pin of interest, it is very important to make sure you have good shielding around that particular pin. So proximity to the nearest low DC resistance shield to VSS pin is also critical and can lead to localized shield performance issues even when the shield has many other point of contact to the VSS pin array. So a test to determine the resistance of VSS pin to the shield is required to determine the quality of the connection. So with ModusTest KGS, we have developed shield performance test. So what we do is we measure every single contact point of VCC to shield. We call it good VSS contact to shield test. We confirm at a very high percentage, more than 80% of VS pins to make contact to shield with sufficiently low resistance value of less than 10 ohm. And limits can be customized depending on your application. But we're trying to make sure all of these VSS pins have good at least 80%, more than 80% of those pins have good contacts with the VSS pin. And also we perform proximity test to make sure the pin of interest that you really need to make sure that they have a good signal integrity, have good shieldings around them. Okay. This is a coaxial socket design validation result. One of the examples that we performed for our customer. On the y-axis, it's a percentage of good contacts. And on the x-axis, it's insertion after 5K, 10K, 15K, and 25K. In this particular example, you can see that the percentage is going down. So as you perform more insertion, the contact between your VSS pin and shielding body is degrading. So with this result, our manufacturer was able to improve their coaxial socket design and eventually help their customer to have a great performing coaxial socket. So with these examples, what am I saying? So this is a graphical description of the impact of ModusTest KGS on production performance. This is typical picture of testers producing good units on production floor. So with ModusTest KGS, what I'm saying is based on our data, it helps our customers to achieve higher first pass yield, final test yield, less yield variations, low retest rates, and higher OEU and utilization, optimize setup debug time, and optimize cycle time and throughput. We have two examples from customers we have. One of the customer, based on their data, they used to take down the setup every day to perform some kind of maintenance to keep the production running. After implementing ModusTest KGS, the frequency went from every single day to 5 to 7 days. So once a week, And the second customer also confirmed that from 3 days, every 3 days, they're taking the setup down. Now they do it once a week. So you can see how much of throughput performance they have improved by not having to take the setup down. So this is a graphical image of, with much less number of setups, you can produce more units because you have huge improvement in your production performance. I've done, it's a simplified ROI analysis. So on top of tremendous saving from higher throughput with less setups and setup debug time reduction, I picked first pass yield impact on your cost. So let's assume that using ModusTest KGS, you improved 1% of your first pass yield. So because every single time you retest, you're basically wasting your test cell resources, right? So if you have higher first pass yield, you're saving it from retesting it. So let's assume that there was a 1% first pass yield improvement. Typically, there are more, but I'm trying to be conservative to make the point with this ROI analysis. And let's say you have 50 setups running on your production floor. And I know you do far more than that, but I'm just picking a number, 1%. So that means 1% times 50, that's a 0.5 tester cell saving for you because you don't have to retest. Okay, instead of retesting, you're just testing new products. And cost of tester is, I assume 300K. Again, nowadays testers cost a lot more than that. 250K for handler. And if you multiply all these, your monthly saving will be around 275K. Your yearly saving is $3.3 million. So conclusion is on top of the savings you already have with less setups and debug time, additional major savings come from first pass yield improvement and volume regardless of pin count and cost. Because some of the customers, we have small packages, so maybe this doesn't have huge impact. But remember that a lot of people are doing multi-site test on production, right? So everything adds up. So with a first pass yield improvement on all sites, you actually have an huge impact on your production cost saving. This is an install base, very interesting data. Install base analysis, we compared between IDMs. IDM means they have their own factories, and fabless guys. And we found that a lot more than 70% of our customers are actually installing this new process in the factories, and they're IDMs. And this is established as a best practice among leading chip manufacturers with hundreds of tools installed in factory worldwide. So this is based on hundreds of tools installed worldwide. We found that a lot more IDM customers are using this best practice in their factories. And we found that based on our interaction with them, having direct visibility to ROI, IDMs employ this best practice in their factories and subcons at a much higher rate than fabless manufacturers. These are some of the customers who are actively using ModusTest KGS in the industry. And we also conducted install-based analysis on socket suppliers. And this is not what I'm saying, but this is what our customers are telling us. So ModusTest KGS design validation, OQC have become prerequisite for engaging with industry-leading chip makers. So you can validate it, right? So I'm not just making this up. These customers are telling us, coming to us and say that, in order for us to engage with industry-leading chip makers, we have to use your testers to validate, their solution, socket and pin solution. So my final thoughts to all of you is, are you still running production without ModusTest KGS? And a few more slides. Here's a website. I'll put this on the chat box later. So this is our website. If you go there, there's a list of products that we offer at the moment, different generations of MPT as well as MTC. MTC is a cycler for life cycle test. And you can also see various range of channels that we offer, channel counts that we offer. The largest one is 29,000 max. And we also have a smaller version of 2,650. And there's an asterisk, and then single asterisk means it's not available for sale anymore. And then double asterisk means it's available in fourth quarter 2024. So currently, we're offering these, these 4 models of MPT, and this is coming out. And in terms of MTC, we're offering the MTC G5 Plus and Max model. I want to emphasize two of the offerings that we have that's coming out. MPT Max, 29,000 channels. It's ultimate pin count, fastest test speed, large test aperture. So it says Q3 here, but it should be Q4. And another offering that's coming out it's called memory. For those of you who perform memory tests on the production floor, so this is called memory DSA checker. So it allows you to perform the check, the integrity check on your DSA board in 128 sites in parallel. So you can test whole suite of 128 sites at the same time to make sure your DSA board that you use in the high-fix board is good for production usage. The last one is it's called Magnus DC. This is for silicon test. It has 29,000 full Kelvin DC parametric test. We believe this is based on our research around 8 times larger pin counts than conventional testers in the market. And plus or minus 15 volt rail, 24-bit measurement resolution, air-cooled and user-friendly. And these are the tests it can perform: open shorts, parametric, all parametric test leakage, capacitance, and mixed signal. This is coming up. And a couple of use cases. If you are testing large package in production, you can do that in 29,000 channels, so DC parametric testing. and a large package substrate testing, large package characterization and qualification. And you can also use this tester for high parallel parametric probe testing. Okay. This is a video image of, hey, Jack, do you want to kind of explain this video?
Yeah, this is actually just a quick video of a life cycle study. I think it ran from 0 out to 800,000 insertions. This is a memory contactor. You can basically see it progressing. We're taking, samples versus test count. Like right here, it's at roughly 400,000, and you start to see some interesting things happen in this socket. For example, picture's worth 1,000 words, and a video even more, because in a quick 5 seconds, 10 seconds, you can tell that we have a boundary issue within this socket over the life cycle. And when we go investigate this particular one, it's the same contact point throughout the array, but the edges wore differently. And in this particular case, there was not sufficient support structure at the boundary of the elastomer, so it failed there because it was essentially leaning. Can you go back to the video?
Yeah, somehow there you go.
I don't know what happened to it. So slide out towards the end.
Yeah.
Yeah. It gets progressively worse, but anyway. So this is just one example of the kind of things you can see with a life cycle test, and by looking at it spatially, there's so much information there versus looking at raw spreadsheets or scatter charts. Having this data set, when you use the combination of the MTC cycler with the MPT to take the CRES information, it's extremely valuable. You can look for planarity. You can see how things are performing spatially. In this case too, there's also a bias towards one side of the package, and turns out their production pusher was not pressing flat across the array. So they had a mechanical bias to one side. So one end of the distribution actually shows some additional wear as well. So just a great example of how the two tools together can give you a lot of really insightful information about what's going on with your socket. And this is all like very similar to being in situ, because it's using your real production housing, your real stack up, everything else, versus a surrogate array for just doing characterization. It's the real stack up you're going to go to production with, right? So.
Okay. And next slide shows one of the examples of the board we built for customers. So as you can see, you can maximize the space. This is a MPT interface PC board. So this particular customer wanted to maximize the real estate. So they designed in multiple different footprints on a single board. And they're saying that we can support all different kinds of package types as well as socket types. And this should be the last slide. This is the picture of we call it Regula. This is a shorting device that we use to create the shorting path for CRES measurement. So we have different types of Regulas that we use, including insulated device simulator for any leakage test. Okay, so that should be it for my presentation. And let me see if we have any questions in the chat. Oh, no questions. Okay. So I guess, does anybody have any questions? Like I said, if you need us, we can always set up a separate call with your company so you can ask, your question like within among with your colleagues. And you can always you have my email address. I sent out invitation through that, or you can also visit our ModusTest website. And let me just put this in the chat box to make sure everybody has access to that. And under company, there's a contact information for US East, Central, West, and Singapore and Malaysia. Oh, maybe I'm not sharing it. Yeah, let me share this. Okay, so under more, this is our website, modustest.org or .com, works both ways. Under more, company, and scroll down, there's a contact information depending on the region you're in. Okay.
Okay, Jesse, it looks like we got a question here.
Okay.
Explain the different types of actuators. I assume maybe he's asking about the different MTC options. Can you hit the website real quick to go to the two MTCs? Bring that up. So right now we have two MTC options that we sell. The MTC G5 Plus, which is compatible with the MPT XT and back, and it'll push up to 1,500 pounds, 1 micron Z resolution, and then we have a new offering that is coupled with our MTC. Our MPT Max tester, which is a little bit larger, of course, so the gantry is a bit larger, and this one goes to 2,000 pounds of total force. It can actually do more, but right now it's spec for that. At 29,000 pins, typical gram force, 2,000 pounds should be sufficient for sockets in that range, right? So we do have a little bit of headroom there, but so I'm not sure if that's what you're meaning by actuator. If you want more detail about that, at the pusher face, the actual actuators, we can adopt anything. We bring TCUs from production test cells. We have multiple different variations from gimbaled style actuation to planarized actuation. It's all a mechanical exercise. Then, whether you want hard stop control or you want stroke control, we can accommodate any of those options mechanically, right? So at the pusher face, and there's a load cell built in, so we have constant force and displacement readouts. Think of it as a mechanical O-scope for the socket, right? I'm not sure if that answers the question as far as actuator types. I'm assuming you mean cyclers, Patrice, but you can reach back out to me. I'll put my email if you want to reach back out to me about that.
Okay. Okay, so well, if no one has any more questions, we can end our webinar here. But feel free to reach out to any of us, myself, our website. Oh, how does MPT support many different socket locations? Jack?
So depending on, we've done parallel test versions where we have a combiner. If it's the same socket, multiple sites, we have a combiner plate. As long as the total force doesn't exceed our capacity, we can have a combiner plate that ties in the multiple shorting devices. And we've done, I think the biggest one we've done is like a 16 site parallel plate, or where it's basically a pusher with many shorting devices on it. We array the sockets out in an array and we push all of them at one time. If they're different sockets, like the one board that he just showed there, Jesse, go back to that multi-footprint. Like this one, the cycler, of course, it has movement on the y-axis, and so it's centered on the x-axis and has movement on the y-axis, so we can actually move it to the MTC G5 actually has X and Y movement. The MTC Max has Y movement, so it's all on the center line. So you can use a multi-site pusher. In this case, this particular customer uses a tri-site, dual-site, single site, kind of a common frame, and so the pusher it's essentially their production lead backer from their handler adopted up underneath our cycler. That way the nesting and everything can be just like their production nesting for the package nest, for the lead in and everything else. Typically you want to try to duplicate as much of that stuff as you can, or you can decouple yourself away from that mechanically and use whatever framework you want. If you're trying, depends on what variables you're trying to tackle, right? Do the tests require customer daisy chain? No, they don't require daisy chain device. We can use your daisy chain devices. We can use your live devices. Live devices we can test with any domain within the silicon. So within a power domain, as long as it has more than 3 pins, or at least 3 pins, power domains, ground domains, any domains that have more than 3 pins, we can use the shorting those domains within the silicon to create a shorting path, or we can have surrogates that we machine, or hybrid regulars that are balled that we use to short. So it doesn't have to have a daisy chain device. It can be purely, typically we use machined metal devices, plated devices with gold plating or solid silver. How you match solder alloy. So we've got lots of data that shows, for example, strong correlation between what using silver looks like and solder ball. Typical solder ball, they're very, very similar, but we can do, from a plating perspective on the Regulus, we can do most any kind of plating. If you want to use a particular plating material, we can use real solder balls too. We plate Regulus with, it's basically a shorted device with balled device with whatever kind of plating or whatever kind of ball, SAC 305 ball, you name it, right? So it's up to you what kind of surrogate you want or what kind of shorting device you want, or you can use your live packages, right? So no, it doesn't require a daisy chain, but we can test those also. Yeah, so we do that often. Full shorted device, and then they'll bring their daisy chain device, and then they'll bring their live package device. So, it's really easy to compare the stand-in shorting devices to the live package, just so that you know that you're getting a representative example, or if you need to have an offset in your CRES test limits for your maintenance, you can quickly see what is the mean difference between live ball versus my shorting device that I want to use for production, for testing all pins. So maybe there's a 5 milliohm difference, no problem. Adjust your limits according to the difference between your shorting silver devices and or gold devices and your production silicon package. So it's quite easy to accommodate the differences.
Okay, so if no more questions, thank you everyone for your time this morning. So have a great day and week ahead. Thank you.
Thanks for joining.